And now fatigue. Todd alluded to the fact that fatigue is one of the issues that are being discussed by Committee T10. T10 is the committee that deals with the concrete bridge specifications, Section 5 of the AASHTO LRFD bridge design specs. Okay, AASHTO is American Association of State Highway and Transportation Officials. T10 is a subcommittee of the subcommittee on bridges. It's kind of a very elaborate, detailed organization structure. T10 is the committee that decides what to change in terms of design rules for concrete bridges, including the use of welded wire reinforcement. So a few years ago, probably early 2000s, about 10 years ago, we were asked by WRI, and we got additional funds from PCI, and we did elaborate testing from different sources to check on the fatigue resistance of welded wire reinforcement with cross welds in the wire or in the specimen and without cross welds. Now the T10 is now looking at a proposal from one of the giants of the industry. His name is John Kulicki. He's the guy who developed the AASHTO LRFD specifications. So he has to be taken very seriously. He's now retired from Majeski and Masters, but he carries a lot of weight, and he did a research project for extending lifespan of bridges. So the idea is to see what provisions you could have to make the life expectancy or the bridge designed for 100 years of life instead of 75 years. Because the current standards says the expected design life is 75. They wanted to extend it to 100. So one of the things that he is saying is that we need to revise fatigue. Now, for you here, what's the impact of that? Fatigue can impact negative moment zone in flexure. That's if you're using it on beams or slabs. It can impact slab bridges and therefore box culverts if they don't have a whole lot of soil fill on top of them. It can impact shear reinforcement in bridge I-beams, which are the most common products in the US. In segmental bridges, which are used in Florida, California, and other parts of the country, you could have a problem if you use welded wire reinforcement, which, by the way, is a growth market. Segmental bridges and tub shapes are a growth market. It could have an impact on principal stresses. Deck slabs is a huge market for you. Fortunately for you, the code says for deck slabs, you don't have to worry about fatigue. I don't know about the Canadian code, George, but when we designed the Canadian bridge at Windsor, we did check fatigue. I checked with my engineers there, and we did check fatigue. Whether we should have or not, I don't know. But that's something that...
historically, whatever we've done for boxes or anything like that, we've had to check.
Yeah. And it controls.
Yes.
So it's a serious issue, even though it doesn't control everything across the board. Working Agenda Item 181, in September 2014, by John Kulicki, was brought to my attention by Todd Hawkinson. I was not at T10 at the time this was discussed. I was there at a convention, but I was distracted going from one meeting to another, so I didn't attend this part. The summary of it is this. As Todd said, for fatigue 1, which impacts us here, for what fatigue 1 limit state, the load factor is changing from 1.5 to 2. That's what, 25% increase? So the loads that you're designing your structures for are increased by the ratio 2/1.5 across the board, whether it's a concrete bridge, concrete structure, any transportation structure, concrete, steel. You take the loads and multiply them by 2 instead of the 1.5. That's one effect. The second effect, they took our beautiful fatigue formulas, if you call them beautiful, because I developed them, so and destroyed them. What they did was, and they have a very scientific justification, which in my opinion, it's just to put stuff in there so that they can tell the world that they have done something. But they took the limits and increased them. So 24 becomes 30, and so on. This is the limit for wires with no cross wires welded. This is the limit for wires with cross wires welded at the high stress zone, the high stress section that you're checking. The good news is they're increasing the limit. So even though they destroyed my baby, this is a good thing for you because they increased the limit. So when they increase the limit and they increase the load, it's a wash. Okay, the load, the demand on one side, the capacity on the other side. I'm increasing the demand, and I'm also increasing the capacity by the same ratio. Okay, fine. If that's what you want to do. It's not going to affect us economically. The alarming part about this is that when you look at the language as you move through the working agenda item, you see some tables in there that reduce the limits. So these tables come from the original report that they submitted as evidence. So someone on T10, because that's all part of the submittal, someone on T10 is going to pick on this because my associates in the company, when I asked them to review this presentation, they said, okay, there's inconsistency here. Which one? So they picked it. So if you do this, if someone on T10 says we want the low limit, then we're in trouble. That's why this has to be watched and has to be watched carefully. Now, the reason I'm saying that the justification they use, which is Monte Carlo simulation and some really fancy stuff, fancy words and life cycle and analysis and all that stuff, is not really what we did. What we did was very simple for the Wire Enforcement Institute. We took a whole bunch of samples from a lot of sources. And we figured that the stress range plus 1/3 of the minimum stress has a lower bound of 16 KSI. So we said the stress range minus 0.33 F minimum the live load 16 KSI minus 0.33 F minimum is the limit of stress range. It's just as simple as that. And when you have wires that are plain, straight wires without any cross welds in them, then the limit goes up to 24. So this would apply to bars. And the first one, and this would apply to wire as well if you're not welding in the high fatigue zone. So in conclusion, I'll leave this slide on here for a second. If you look at it casually, no action is required. If you look at it a little more seriously, you need to be very vigilant, you need to be watchful, and you need to attend these meetings to make sure that if they make the change, they stick with the change they propose in the working agenda item, not the background information that's attached to the working agenda item. It's probably a little bit on the light side now that we've gone through fatigue. There have been numerous applications in the past 20 years and the credit goes to your very active members. I have to single out Dyke Starnes. Dyke is one of my idols. So he really works hard. And when I was in Florida in 2007, 2008, we teamed up and we went to Tallahassee, and he's tireless. And this has been a help to the whole industry. And I also have to brag about Nebraska. This standard was introduced in 1992. I consider it the gold standard. It made it to the PCI Bridge Design Manual. It's what people use most of the time, unless they get to be too fancy. That's what people use in detailing I-beams. You could see that everything here is welded wire reinforcement. Everything, nearly everything, almost everything. The only thing that's not welded wire reinforcement is this tiny number 3 bar. Everything here, this is WWR, this is WWR, 2 U-shapes meshed together. This is the main reinforcement, WWR. The top flange reinforcement is WWR. And you see that you have 2 wires at the top, minimum 2-inch spacing. These happen to be a little bit longer. And these are 2 wires at the bottom. An excellent detail. It has served well. I was sitting at, I was on sabbatical that year with a friend at HDR's office in Omaha, and we sat down and developed this standard, and it worked very well. It has worked very well. In the PCI Bridge Design Manual, that's what's guiding people to do. A recent development here that I think I like, but I need to get your reaction because it hasn't been done before. This is going to be the first time it is done. If the concrete option wins and if this detail is adopted, is to take the cross wires and put them above the cross section. When you do that, you have more anchorage. You have more anchorage of the wires. And we have a kind of a stay-in-place deck form here. So the stay-in-place deck form will be below these anchors and they will go into the deck. So that's a detail that we think we've already gone through the initial screening and it seems that everybody's happy with it. The rest of the details are very similar to what's being done now on Bogey Creek Bridge, supplied by InSteel. 1 U-shape here and 1 U-shape here. So applications on bridges, Platte River East, Arbor Road, so many bridges, it's the standard in Nebraska. Herb Gray Parkway, that is a major $1 billion plus project in which the welded wire reinforcement was introduced by the designer in the design stages, but then our company added a lot more because they were only doing welded wire mesh in the webs. We converted everything to welded wire mesh. Abu Dhabi Airport, that's a major multi-billion-dollar project, and some of the loads are just horrendous, extremely high loads on it. And so we converted about bridges about the total cost was $150 million for our section that was precast. But the whole project was more like $15 billion. And this is my favorite picture. It's my favorite picture. I don't know how old it is, but it has to be one of the early applications. You guys tell me, more expensive, less expensive, all this discussion yesterday. Come on now. Nobody can produce a rebar construction with this quality. Nobody. Nobody can produce a rebar construction with this wire spacing, this narrow wire spacing, which helps crack control. And you could see here, And then when you add to this the fact that production of the I-beam itself in the precast yard gets reduced, the labor gets reduced by 30%, 40%. That's your selling point. Don't sweat the per pound cost of your material. That's not the issue. The issue is to convince designers to use it. And if designers use it, everybody will fall in love with it. That's the issue.